Thank you very much for the invitation. What I'll be talking about is kind of work that I did about 3-4 years ago. The preprint is on the archive, and it was already this is already published work with my colleague Dima Rinkin and my former student Marci Havlicek, who's just finishing now a postdoc at UPenn. So it's a bit of an old story, but I thought this is a so it's okay, hopefully. So I want to discuss about there are two results in algebraic geometry where the end result seems to be the same, but they're in very different contexts. The statement in both cases is the fact that a certain differential graded algebra is formal. And so I let X be a smooth projective variety. And the meaning of the word being formal is the statement that you have this complex of sheaves, and you say that it's formal if when you replace it by the complex of cohomology sheaves of it and put zero differential, you get a quasi-isomorphic complex to it. This is not the usual statement that people use in the DG algebras theory. Usually when you talk about DG algebras, you're working over a field, and then any complex over a field would be formal in this sense. If it happens that the thing had an algebra structure, you would like the quasi-isomorphism also to respect this. This, even over a field, it's a stronger statement. And there are two instances where there is formality. This one is about the Rham complexes in positive characteristic. And this goes from the celebrated paper of Delin and Deluzy in 1988. And there's a paper of August and Vologodsky from 2005 where they prove a stronger version of this. And there's another sequence of papers, one with Dima Rinkin myself, and one with Dima Rinkin and Marci Havlicek in 2010 and 2014, where we prove formality for a completely different kind of guy, namely the structure sheaf of a derived intersection of two subvarieties. And the conditions in both theorems seem to be somewhat similar. So Mircea Mustață around 2010 asked if there is a way to take one of these statements and recast it in a way that you can make sense of it using the other statement. So this is what I'll talk about today. So let me begin by reviewing a little bit algebraic de Rham cohomology. So you start with this algebraic de Rham complex, which I've written here. The terms are the sheaves of holomorphic.
It's not the formality, is it for complex or algebra?
Sorry? It will turn out to be both of them will be for algebras. For complexes, both complexes that we will prove formality for, they will be DG algebras, and we will prove formality for these DG algebras. So, but the hardest thing, so if you're looking at complexes of sheaves, it's very hard to even prove that the complex itself is formal, even ignoring the question of. So on a scheme, most complexes are not formal. Forget about the DG if it has an algebra structure or not. So we will prove that there. Okay. So you start with this complex, which is you just take the sheaves of holomorphic forms and you put the de Rham differential. And you define the algebraic de Rham cohomology as the hypercohomology of this complex on X. Now, the reason this is interesting is because Grothendieck proved in a stronger situation, but certainly for a smooth projective variety over the complex numbers, that if you take X as a scheme, so with its Zariski topology and no analytification, anything, you compute, this is a complex of sheaves of abelian groups on X. You compute this hypercohomology, it happens to be equal to the Rham cohomology of the analytic space associated to X. So this is a way to recover the de Rham cohomology with complex coefficients. Now, a few observations about this thing that we are doing here. First of all, the complex that I wrote, even though it looked at first that it was a complex of coherent sheaves, is not a complex of coherent sheaves. The main reason is that even though the objects themselves are coherent sheaves, the maps between them are not maps of coherent sheaves because they don't respect the OX linear structure. The second thing that you should note is that unlike the smooth case that everybody is, this looks a lot like the smooth case. And in the smooth case, the de Rham resolution is a resolution of the constant sheaf C. This is a resolution of the a consequence of the Poincaré lemma. It's exact. The complex is exact, and also the sheaves of smooth forms would be fine. So they would have they would be acyclic for the global sections functor. But in our case, we know that omega I is not a fine sheaf. This is a sheaf of holomorphic forms, and so this has cohomology. That's why we have Hodge cohomology. So it's not a resolution of anything. So it's not at all obvious that this would compute the cohomology of. Nevertheless, Nevertheless, we have Grothendieck's theorem, which is a bit surprising at first. Then you understand. Then this can be if you write down the double complex corresponding to the Dolbeau resolution. So maybe I should explain how Grothendieck's theorem works, at least intuitively. If you tried to, so hypercohomology of something, you try to resolve the things that the complex that you have does not have, the sheaves are not acyclic for global sections. So you try to resolve things by acyclic things. And the way you do it is you put the Dolbeau resolution of everything here, A1, 0, A1, 1, and so on. And you can lift this map, which was here, the de Rham D. We notice that it is really, here I have the del bar operator, and here I have, if I put the del operator here, I will get the de Rham D. The del operator on a complex manifold will. So now, if I take if I take the total complex of this bicomplex complex holomorphic setting, this will provide a a fine resolution of this complex. The total complex of the bicomplex will give a fine resolution of this complex, and then I can take hypercohomology, and the hypercohomology will be exactly the de Rham cohomology with complex coefficients. On the other hand, this is just one particular resolution that I can use of this complex. So I could have used any other resolution, and the hypercohomology would have been the same. But this proves that the you need to Agat for a comparison between the analytic computation of the hypercohomology of that complex. But that's the general idea of Grothendieck's theorem. All right. So once you have this definition of the algebraic de Rham complex, you have automatically a Hodge-de Rham spectral sequence whose E1 page is HP of omega Q, the Hodge groups, and converging to the de Rham cohomology. And this simply comes from the fact that the complex here at the top is, you can do the stupid truncation filtration on it. And the associated graded pieces of it will be the omega I. And so the spectral sequence to this filtered complex gives you the spectral sequence that you want.
Is there a sense of R in R gamma here?
What?
Right derived.
Right derived functor of the gamma of the global sections functor. I don't want to apply the global sections. So I have this complex. This is my de Rham complex. I could conceivably apply the the global sections functor everywhere, but I would get nonsense. What I'm asking to take the right derived functor as defined on derived categories, and the meaning of this secretly is replace this by a complex which is quasi-isomorphic to it and consists of acyclic elements for them. Yeah. Okay. All right. So this is a Hodge-de Rham spectral sequence in its most bare form. And over the complex numbers, if the manifold is smooth and compact, this spectral sequence, we know that it must degenerate at E1. And the reason for that is if it did not, the terms in the terms that you have at E1, the total sums of them would go down at some point, and you would get something smaller in dimension. It's simply a dimension count. So this says that after the E1 page, nothing can happen. All right. So now the question is, how do you prove this? This was a big open question. How do you prove this without smooth method? So this was a big failure of algebraic geometry, in the sense that you can prove that the statement that this spectral sequence degenerates at T1, all the terms are defined purely algebraically, but you would like to have an algebraic proof of this statement. And this was the result of Delaunay and Deleuze, which I will try to explain quickly. So the first issue is you would like to work with complexes of coherent sheaves. And you do not like the nonlinearity of D. And the answer is, let's forget completely about the fact that we're trying to solve a problem in characteristic P. And let me set here a few of the definitions. I have the relative Frobenius map, which goes from the variety x to x prime, which is called the Frobenius twist. I don't know, have you guys gone over this stuff in? So x prime briefly is just x, but I have changed the way the scalars on k act on it. They act by 1 over p's power. So x prime as a scheme is the same as x, just because the map raising to the power p is an isomorphism at the level of k. But they are not isomorphic as k schemes. And then one way to think about the map from x to x prime at the level of functions, I can just think about ox prime as the subset of the functions inside ox, which are p's power. Of coherent sheaves, the maps were not ox linear. The complex does become, the maps after the push forward do become ox prime linear. I will exemplify this in a minute, but this is a very easy statement. And the harder statement is the statement that the resulting complex, its cohomology is the ice forms on x prime. Okay. All right. That's the first theorem. That's general. That requires no assumptions on x at all, just as long as it is over an over a perfect field of characteristic P. The second statement was due to Delaunay and Deleuze, which requires some assumptions, namely that you're working in high enough characteristic, bigger than the dimension of x. And secondly, that x admits a flat lift to the ring of second Witt vectors of k. If you want to think about being over Z mod P, this would say that the variety admits a flat lift to Z mod P squared. This is not in any way automatic, but many varieties that you you might be interested in do satisfy this. In particular, maybe let me say, if the variety came from a variety defined over Z, it would automatically, so flat over Z, it would automatically have an extension from Z mod P to Z mod P squared. You just take the original variety, reduce it mod P squared. Secondly, even if it was only flat over some open, if it was defined over Z and not maybe just flat over some open set, that would be enough to guarantee liftability over most of the primes. So if you go far enough, it would be enough. And that will be enough to prove what we will need in characteristic 0. So the second statement, the statement that Dallin and Deleuze prove is that with these assumptions, after you've pushed forward the de Rham complex, you get actually a formal complex. So not only the most important statement that you need. From this, it follows almost automatically that the Hodge theorem holds in characteristic 0. I can explain how this last deduction is, but it's not very important. The point is that the hypercohomology of this complex, on one hand, is the same thing as the hypercohomology of the original de Rham complex, because push forward and hypercohomology commute. On the other hand, the right-hand side, you can compute the hypercohomology, and it gives you just the dimensions are the HPQ numbers. And these do not depend on a particular k-linear structure on X or X prime. And because X and X prime are abstractly isomorphic, that gives you that the left-hand side has the expected dimension. And once you know that it has the expected dimension, you know that the spectral sequence must degenerate at E2. Once you know that it degenerates at E2 for sufficiently many primes, so this is if your variety comes from a variety over Z or some finite extension of Z, you know it over C by some kind of general principles. Are there any questions about the statement of this theorem?
Yeah, so the point at which I start using that X is
this is the main statement that you care about. You want to show that this Frobenius push forward of the de Rham complex is formed. That's the crux of the proof. All right. So let's do an example just to yes.
So hello, symplectic geometry. So this is the relation between the S1 equivariant and the non-equivariant symplectic homology in characteristic P, for which we do have proofs. So they don't look anything like this.
I would like to understand your comment too. Okay. All right. So let's do an explicit example in the simplest possible example. Let's take the line. As I said, the statement holds for even quasi-projective varieties. Take the line over Z mod PZ. And the functions on X are the polynomial ring in one variable. The functions on the Frobenius twist are the piece powers, the polynomials which are piece powers. And because K is perfect, the coefficients, you can always take square roots, but piece roots, but only you can take piece roots of X to the P. So the polynomial in X to the P are those powers. And this is a relative Frobenius. And just the inclusion of the polynomials in X to the P. And the algebraic de Rham complex is just this complex. It has only two terms because it's one-dimensional. And here's what Dallin and Deleuze and Cartier tell you. Maybe before I go this, let's do a quick calculation by hand. So it's very easy to see what. So first of all, so we have this de Rham complex. on the line. Now, we can calculate the cohomology here. It's really easy. What functions have their derivative equal to 0? What polynomials have derivative equal to 0? Well, the answer is they would have derivative equal to 0 if they were constant, but not just constants because we're in characteristic p. X to the p also has derivative equal to 0 because the derivative is px to the p minus 1 and p is 0. So the kernel here, so kernel of t is k bracket x to the p. That's not so surprising, even though it's maybe a bit surprising because it is very different from what happens in characteristic 0. But what is the co-kernel? So the way you should think about it is what polynomials I cannot find an integral of them. And of course, in characteristic 0, every polynomial can be integrated. But in characteristic p, x to the p minus 1 does not have an integral, because the integral of x to the p minus 1 would want to be x to the p over p. So there is a co-kernel here. Is basically the stuff that's generated, it must be it will be x to the p minus 1 k bracket x to the p. So also x to the 2p minus 1 will not be integrable and so on. So dx, if you want. So that's the statement of Cartier. The statement of Cartier says that the cohomology of this complex is in degree 0 k of x to the p, and in degree 1 it's p rank 1 module over k bracket x to the p. In this case, the generator is x to the p minus 1 dx. Now, the statement of Delaunay-Lozi is a stronger statement, namely that I can actually take this complex with 0 differential. This is you can think about as the direct sum of omega I x prime. This is O of x prime, and this is omega 1 of x prime. And I can map it quasi-isomorphically into this other complex with non-zero differential. So I can find a quasi-isomorphism between this complex and this complex, where this complex is the formal version. And this is this Cartier map, which sends d of x to the p to x to the p minus 1 dx. So at first, when I wrote this, I got myself confused, and I said, well, how can this be? D of x to the p should be p dx, px to the p minus 1 dx. And so it should be 0, but it's not, because here in this ring, we don't have any dx. X does not exist. Only x to the p exists. That's a generator of this ring. Okay. So this is an explicit calculation showing you Delaunay-Lozi for the line. All right. So now let's completely move away from this story. I've told you at least the statement of what Delaunay-Lozi tried to prove, that the push forward is formal, here as in this example. Let me move to a completely different story, which is that of derived intersections. So you take two smooth subvariety of a smooth space S. Now you could be in characteristic 0. You could, well, not quite any characteristic, but characteristic 0 also works. So if you wanted to intersect the two subvarieties as a subvariety, you would just take the tensor product of sheaves. That's what I call W0, and that I would call the classical intersection. And on the other hand, we can take the derived tensor product, and if you compute it carefully, you can actually give the structure of a commutative DG algebra. When you do, and so we've got some object which looks like to be the structure sheaf of a space, but it's not a sheaf, it's a complex of sheaves. And it can always be endowed with the structure of a commutative DG algebra. So I want to think of it as defining a thickening of some sort, a DG thickening of some kind of enhanced geometric object which is the DG scheme, which is the derived intersection of x and y.
I can't even see an algebra structure. That's my problem.
Well, so what do you need to do? You need to resolve OX by a free OS DG algebra, or locally free OS DG algebra, and then tensor with OY. Is your concern local or global? Let me ask that.
No, local.
Locally, X is smooth. I can write it down as a Koszul resolution. I can write down X is a local complete intersection, so locally I can write it down as a zero locus of a section in a vector bundle. Write down that the Koszul complex you can think of as a commutative in the graded sense, a commutative DG algebra. Now when I take that DG resolution, which has an algebra structure, when I tensor it with Y, it will still have an algebra structure. Okay? Any other questions? So I like to think about this as just as an infinitesimal thickening of W0. We will see that there is an ideal, the ideal which cuts, so W0 can be thought of as a, OW0 can be thought of as a quotient of OW, and the ideal that cuts out this subvariety is actually nilpotent. So this, if you're happy with replacing, sorry, if you're happy with replacing algebras by DG algebras, this is not enough thickening of the original algebra. All right, let's do an example. I'm going to take 2 copies of a point in the line. So I need to sheaf of the second point, because I'm trying to compute the tensor product of this with itself. And what I get is this complex. So if you want to think a little more invariantly, you could think this is O of W0. Just the intersection of a point with itself is just a point. But the derived intersection, you can think of it as a symmetric algebra over W0 of the conormal bundle of S. This just comes from the fact that if you do calculate this for an arbitrary x, but x is still equal to y, s can be arbitrary, this first term here, the cohomology at least at this point, will be the conormal bundle. So the symmetric algebra of the conormal, so what you're going to get in general, you'll get something that looks like so you'll get a complex which at least its cohomology sheaves are O of W0, conormal bundle of x inside S, wedge 2 of the conormal bundle of x inside S. So these are the cohomology sheaves of O of W are listed here. So I can't promise that the complex is quasi-isomorphic to this, but if it was formal, then this you can think of, if you put 0 differential here, this would be the symmetric algebra on the conormal bundle of x over S shifted by 1. Does this make sense?
This is general whenever you take x intersected with x.
X intersected with x, yes.
Okay.
So this is a self-intersection case. That's why there's only one x, there's no y in here. And the nice thing about this is that I can make a geometric analogy that if I have a space whose ring of functions space of the W will be the total space of that vector bundle. So I really want to think of this self-intersection as the total space over W0 of the normal bundle. But the normal bundle somehow is shifted by -1. It's some mysterious thing. So here's a theorem that I proved with Dima and with Marzi. So as in more generality, if now you're trying to intersect two things, x and y, the cohomology sheaves will still be exterior powers of something, and the something is the excess intersection bundle dual. That was known for a long time. This is a stronger statement. It says that if you have some characteristic, that the characteristic P is either 0 or bigger than the dimension of the ambient space, and this exact sequence splits. In other words, that's the obvious exact sequence into which E fits. If that short exact sequence splits, then OW is formal. In fact, this statement is an if and only if statement. Yes?
Sorry, give me a second.
Is this formality as
TX.
Sorry?
is this formality just as algebras or as
As DG algebras.
so not as the infinity algebras?
We never thought about the algebras, honestly. Possibly, but I don't know.
I mean, the question is about if it's as commutative.
Sorry?
Characteristic zero.
That's the same. Yes, the
In
infinity.
characteristic zero, are they formulas commutative?
That's the same question.
In characteristic 0 are,
Is the formula DGA?
that's what he asked, and I have no idea.
Okay. So plus means it's not the direct sum, right? It's the
Plus, here,
that's
yeah, this is not never, if it was a direct sum, that would say that E is
the
0.
kernel, right?
Yeah.
Yes. So
So, right.
Okay.
So this is you take the span inside the tangent bundle at each. So this short exact sequence lives on W0 on the intersection. And on the intersection, you have three spaces. You have the tangent space to the ambient space, and the two tangent spaces to the subvarieties. You look at the span of those two things inside the bigger space, and it has a cokernel. The cokernel, being a vector bundle, is equivalent to the intersection being a manifold. And it would be clean if this E was 0, and it's not.
can I ask you?
Sorry. Yes. Sorry. Yes. Which is equivalent to saying that W0 is scheme theoretically smooth.
Just as a complex of sheaves, what happens if the assumption fails? I mean, you could just say, well, I replace E
Yes.
by this two-step Tx plus Ty and Ts. Is
I-
it true that OW is the direct
I
sum of these
think
pair products?
but I'm not sure. I don't know. I'm not sure. I don't know. But the statement is actually if and only if. The way I wrote it, it's only if, but it's if and only if. Okay.
Does this have anything to do with lifting to W2?
That's exactly my next comment. It doesn't have directly to do with the fact. So at least if x is equal to y, the splitting of the short exact sequence is equivalent to the fact that the normal bundle can be lifted to a flat bundle to the first infinitesimal neighborhood of x inside S. So you've got x inside S. So here's x. Here's inside S. And you take just the first infinitesimal neighborhood. On X, you've got this particular vector bundle, which is a normal bundle. You're asking, is there a vector bundle on the first infinitesimal neighborhood whose restriction to X is the normal bundle? And that is equivalent to the splitting of that short exact sequence. It's some deformation theory argument. So this is similar, even though not exactly the same condition, just to the fact that X should admit a flat lift to W2 of K, in the sense that you're trying to lift the variety. The difference between the first and the second statement is that the first statement is a linear statement, while the second one is not. In the first case, you're trying to lift a vector bundle, which is a linear object, while in the second case, you're trying to lift a scheme, which is a nonlinear object. They're still somewhat similar. So Mircea Mustață asked if there is a way to take the statement of the Lini-Luzi just to deduce it as a purely formal consequence of a derived intersection problem. So the answer is yes, but we need to extend. So far, we've extended the notion of a space in one way by saying that we allow derived schemes. Now I want to extend the notion even more by saying I want to allow, for me, a space will be a space with a my algebra. Together with a sheaf of Azumah algebras on S. So I don't know if people know here, this is maybe not a familiar concept so much, but an Azumah algebra is an algebra which locally et al. Looks like a matrix algebra, a sheaf of matrix algebras. So locally it's a sheaf of matrix algebras, but it might not be globally a sheaf of matrix algebras. What the effect of that is that locally the category of coherent sheaves on X is the same thing as the category of coherent sheaves of A modules, just because there's a Morita equivalence between matrix algebras and OX algebras, but not globally. So what is very different in the case of Azumaya spaces is that the morphism consists of two pieces of data. One is a map of schemes of the underlying schemes, but I also need to give a Morita equivalence between the pullback of modules from one space to the other. So in fact, if you look just for a few minutes at this definition, you'll realize that Azumaya spaces don't form a category. They form a two-category. Because you have between morphisms in the sense that Morita equivalences are given by certain bimodules, and you will have maps between these bimodules. So maybe the most trivial observation here is that so an ordinary scheme thought of as it can always be thought of as an Azumaya space, but even when you do that, the embedding is not fully faithful. There are more automorphisms of the scheme itself, namely tensoring with a line bundle now becomes an automorphism of the Azumaya space that was. So let me give you the most basic example of a map of Azumaya spaces. It's what I've described here. You have an Azumaya space and a subvariety of this Azumaya space on which the Azumaya algebra splits. In other words, you say that an Azumaya algebra splits if it is globally the endomorphisms of a vector bundle. So in that case, you can think about a morphism between the ordinary variety XOX and the Azumaya space SA, which just takes first XOX, maps by an isomorphism into XA restricted to X, which then maps into SA. I think it's yeah. Does this make sense? So somehow the nice thing is that if you have a subvariety of an Azumaya space on which the Azumaya algebra splits, I can think of that subvariety as an ordinary space. I can think of it either as a subvariety of the twisted space or of the untwisted space. So how is this helpful? I can ask now the following question. Let's say I have a smooth space with an Azumaya algebra on it, and I have two subvarieties of it, such that the Azumaya algebra splits on both. I need to have one extra condition, namely that the splittings are compatible on the underived intersection. So the vector bundles which give me the splittings are equal on, are naturally isomorphic on the underived intersection. Once I have this, I can consider x and y as subvarieties of either the untwisted space or of the twisted space. And I can consider their intersections in both of these spaces. So I can compute the untwisted derived intersection and the twisted derived intersection. Now, the same deformation theory argument as before will tell you that the two, so both of these will be ordinary DG schemes. There is no twisting there. Even though you've put this twisting on the ambient space, x and y were untwisted spaces. When you intersected them, you got an untwisted space. So you've got two DG schemes, and you can immediately calculate that their cohomology sheaves are all the same. They're just exterior powers of some excess intersection bundle. That calculation is a local calculation which does not rely on it being in any particular way an Azumaya algebra or not. However, what you would like to know is that maybe you knew that one of them was formal. You'd like to deduce that the second one was formal.
Why can you intersect some varieties in an Azumaya algebra? You can't tensor algebras over a non-commutative.
But right, but you're saying how can I tensor modules? The point is that there's a natural way to take an A module, a left A module, and turn it into a right A module for Azumaya algebras.
But this won't give you an algebra, it will just give you a module.
You're asking what?
The W bar should just be thought of as a module.
Fair enough. I'm happy to think about this just as a complex of sheaves. All right. So now the question is, this seems like a very formal setup, and what does it have to do with anything? The fact is the following, that if I'm looking at a scheme, a smooth scheme over a field of characteristic P, and this is very special in characteristic P, then the ring of differential operators is an Azumaya algebra on the cotangent bundle of the Frobenius twist of x. So that's the unexpected statement. And moreover, this Azumaya algebra, which is a ring of differential operators, splits on the zero section of the cotangent bundle. I will do an example. So let's do an example of this, so that hopefully not everybody is lost. So you start with the line. The functions on the line are k bracket x. The ring of differential operators is the Weil algebra generated by x and d, x and del, okay, with that commutation relation. Now, in characteristic 0, if you were thinking about characteristic 0, d would have virtually no center. Only the constants would be in the center of the Weil algebra. But in characteristic P, something miraculous happens related to the fact that the derivative of x to the p is 0. There's a huge center of d. So the center of d is actually the polynomial ring in x to the p. So x to the p, you can see that it commutes with everything. And in del to the p doesn't do anything. So both of them are central. And if you try to call, this is the directly.
Del to the p kills the functions.
Right. However, I don't think of it as an operator. So I don't think of it as an endomorphism of k bracket x. I think about it as a formal symbol which satisfies us. So this is what these are those things called crystalline differential operators, where so there's two versions in characteristic P. There's at least two versions of differential operators. One is the analog of the Weil algebra, where there's a symbol del to the p which is not 0. But there's also another version where del to the p is 0, but there's a symbol called del to the p over p. This is the version which is it's the universal enveloping of the Lie algebroid Tx. So when you try to take this ring of differential operators, think of this as a module, as an algebra over k of x, k bracket x to the p del to the p, and you restrict it to the 0 locus of this, which means you mod out by del to the p. You can immediately calculate that this is isomorphic to the endomorphism over k bracket x of this vector bundle, which is the Frobenius. D over this is kind of rank p squared, and this is rank p over there's the relative dimension is p, and so the endomorphism will be p squared. Okay, so now we can rephrase the question that we cared about. So I'm going to start with the ambient space being the cotangent bundle of the Frobenius twist of x. So I start writing characteristic p. I take the cotangent bundle of the Frobenius twist. I think about making it into an Azumaya space. I quantize this in Tony's language from this morning. I quantize this by taking the functions on it and changing them to this Azumaya algebra D. The nice thing is that in characteristic P, we have this finite rank algebra. It's not infinite rank. So it's, and on the subvariety, which is a 0 section, D split, so I can think about this, the ordinary x prime completely untwisted. As the 0 section, I can think of it as a section as
I don't know what D is.
D is a ring of differential operators.
Okay.
So I took the ring of differential, so I started with an x, which never appears here, unfortunately. D is the ring of differential operators on x. It has a big center, which are functions on t star x prime.
Yes.
I think about, therefore, I can think about D as an Azumaya algebra on t star x prime, and now I have a twisted space.
So this is just S and S bar are just the definition of the Azumaya space.
Yes,
Okay.
exactly. And because this Azumaya algebra splits on the 0 section, I can think of the 0 section as the ordinary 0 section as either a subspace of t star x prime or a subspace of the quantization. So if you want to think about the cotangent bundle of x prime, it has a 0 section. Now I quantize it to D, and the subvariety survives the quantization. Not every subvariety would survive, but it does survive in this case. And I can now try to self-intersect either the 0 section with itself or the 0 section with itself in the quantized setting. And the answer is that if I do the boring one without the quantization, just a calculation with a Koszul complex tells me that I get that complex on the nose. It's just a direct calculation. On the other hand, that the dual, at least, of the structure heap of W bar is the push forward of the de Rham complex. So if you can show that under this quantization nothing has changed, you will have proven exactly the Ligny-Louzis main theorem, namely that this push forward is formal. So we have a theorem which compares OW with OW bar with some assumptions, and those assumptions are exactly the extendability of the structure of the normal bundle to the first infinitesimal neighborhood. And when you analyze what it means for the normal bundle to extend to the first infinitesimal neighborhood, that is exactly the extendability to W2. So the condition is exactly the same. You need the Azumaya, you know that Azumaya algebra splits on the 0 section. You ask, does the Azumaya algebra split on the first infinitesimal neighborhood? That's what it means. You need both O and N in some sense, and you want O to extend to the first infinitesimal neighborhood. And the Asma algebra splitting on the first infinitesimal neighborhood is exactly extendability to W2. Okay, so let me stop at this point and see if there are any questions, because I'm going to start on a new topic. So what I've done is basically...
Questions, guys?
I've just recast of Deligny-Lousy in this new language where I'm saying what Deligny-Lousy says is takes the zero section in this cotangent bundle and self-intersect it with itself either before or after quantization. If you get the same answer, then you know that compares the Deligny-Lousy things.
These things are algebras, I mean, automatic?
They do have algebra structures. I don't really care about their algebra structures. They do. Yes, I think they do have algebra structures. For the Deligny-Lousy statement, the algebra structure.
It happens here because there's some additional Lie interpretation.
So the conclusion of Deligny-Lousy or Hodge is that there's some numbers are equal to each other.
Yes.
And for the more general derived intersections, are there?
Yes, so that the numbers that you would have for derived intersections would be that if you try to calculate the dimensions of the x between OX and the OY, they would be the direct sum of cohomology groups of some exterior powers of the excess bundle. So here's maybe the statement, the numerical statement. You take global sections of what you want, and that would be that the dimension of xi on S, OX, OY is some, I might get some numbers wrong, P plus Q equals to I, HP of X wedge Q of E, something like this. Or maybe, yeah, E.
Spectral
Yeah.
sequence degenerates always means dimensions on the one page are the same as the total dimension on the
Right.
Are there any other characteristic examples besides zero section and quotangent bundle?
Sorry? Are there other examples of where things?
Yeah, what's another really
Oh,
interesting?
the diagonal and
The
itself?
diagonal and itself in X cross X.
Is that different?
It's fundamentally different.
That's okay.
That's another quantization of the tangent bundle, if
That's
you
the
want.
global Hochschild-Rosenberg.
Yeah, yeah. Here's another example. You take the fixed of take a finite group action, and you take the fixed locus of the group action. That subvariety sitting inside the big variety will satisfy this.
How about complex Lagrangian submanifold inside a complex symplectic manifold?
I think this, I don't know, but I've heard this question asked many times. I don't know. That would be, I think Richard Thomas has been telling me that there's a conjecture that spectral sequence should degenerate.
Can you go back to the criteria?
Yes. Sorry. You want the short exact?
Yeah, the short exact sequence, right?
Yeah. Sorry. Here. Here.
Right. So we have the so you have the tangent bundle of the Lagrangian inside the tangent bundle of the symplectic manifold and the normal bundle of the Lagrangian. Yeah, this seems to be no obvious reason.
But E is zero in this case, right?
Not if the
E is
intersect.
the normal bundle. You just take the tangent bundle of the complex Lagrangian So the only thing that you know is
He's
that
trying to do
normal
the
bundle
self-intersection.
is the
So
cotangent bundle.
X equals 1 here.
Yeah,
Yeah.
x equals y. Sorry.
Sure.
I'm just going to derail it temporarily.
No problem.
Asking you so we might just as well. So it's 0, TL, TM restricted to L, and there's the normal bundle, which is isomorphic to T star.
Right.
This is the dual you take the symplectic
Yeah.
form, and you restrict it to here. Okay, and so the splitting criterion for splitting is something like this.
Mm-hmm.
Okay, which is H1 of TL tensor TL.
Right.
Okay. These are So if you have a Lagrangian subvariety, then you have something such that on the overlap of two charts you get TL tensor TL, a tangent bivector bundle, and this is what we're looking at. You might have to use something. Some people would probably say that no, what you should do is the derived intersection of square roots of the canonical bundle placed on the Lagrangian.
Okay.
But I don't know why I would say that. Some people then it's not going to help you enormously, but it's going to put some additional
Sure.
stuff in there, a copy of the canonical of the manifold. Okay, now at least we understand why it doesn't
Yeah.
follow obviously. So,
Okay. All right.
okay, good.
Sorry. Let's try to. Okay. So I want to now talk briefly about a more general result, which is you would like to not do this just for de Rham cohomology, but for twisted de Rham cohomology. So what is twisted de Rham complex? You start with a quasi-projective variety now, and you fix a regular function. This is what you would get for a Landau-Ginzburg model. You take this complex, where you add, instead of just putting the de Rham d, you're adding the operation of wedging with df. So plus df, I mean the thing which wedges with df. And it's again a complex. It's very easy to check. And the hypercohomology of this complex is what we call the twisted de Rham cohomology of xf. And there's another interesting complex where you just forget to write the d. You just wedge with df. The first complex is, again, not a complex of coherent OX sheaves because it's not OX linear. The second one is OX linear. It's much simpler to understand. And Baranikov and Kontsevich claimed, and then Saba proved, that for any f, you have that the hypercohomology on the left is isomorphic to the hypercohomology on the right. So this is a difficult theorem to prove. And you should think about this as the analog of the Hodge-de Rham degeneration. At least if the critical locus of f is isolated, perhaps even in more generality now with more technology. I don't know exactly what the state-of-the-art technology is, but you can think about this as a Hochschild homology of the category of matrix factorizations, and this as the of the category of matrix factorizations, and that isomorphism would be giving you the degeneration of the Hochschild to cyclic spectral sequence. So I know this only in the case when f has isolated critical points, but I was told that this should hold in higher generality. So the question is it possible to prove this Baranikov-Kontsevich claim using the techniques of derived intersections? So the idea is that instead of intersect the zero section with itself, we can think of the zero section as the zero locus of the zero, as a graph of the 0, 1 form. You can intersect the zero section with the graph of df. And you do the calculations, and the untwisted intersection computes, again, when you take the dual, it computes one of the complexes, and the twisted intersection computes the dual of the. So you would like to say this complex is quasi-isomorphic to this complex. That would be enough to guarantee what you want. These two intersections, one before quantization, second one after quantization, compute what you want. So there is a problem. So now we'd like to prove that these two derived schemes are isomorphic, but the trouble is that neither of them is formal anymore. Before, what we really proved was that one was formal, the second one was formal, therefore they were isomorphic. But now neither of them is formal. So essentially, August and Vologodsky gave a proof of this, not in this language, but they gave a proof of this in their 80+ page paper. We have another proof of this using some other techniques. But we have to essentially use this, which kind of ruins any kind of claim that we have a new proof. But I want to tell you this elementary problem just as I end this talk, because it's an absolutely elementary problem. Anybody could spend some time thinking about it. And it's the kind of problem that sucks you in. We haven't been able to prove it, even though it's. So the question is the following very straightforward problem. You have a regular function of smooth quasi-projective variety over a field of positive characteristic. And the question is, I would like to construct a solution to this differential equation. If you didn't put the mod I, this would just say that g is e to the f. That's all there is, right? The differential equation says that d log g equals to df. That means log g equals to f plus some constant maybe. G equals to e to the f. Now in characteristic P, if you tried to write down the power series of e to the f, you would be stuck at the P's term, because you cannot take f to the P over P factorial. And you can use that to actually prove that there is no solution to this if you don't put the mod I. But the statement is that we only want to solve this in a neighborhood of the critical locus. And so that's what I'm saying is, if you didn't put this P's power here, this would be the critical locus of f. And I'm taking this funny P's power of the ideal, where I just take the generator to the P's power. In characteristic P, that's not the same thing as taking the ideal to the P's power. But it's some intermediate thickening of the critical locus. So the question is, can you find locally around the critical locus of f an exponential of f? Locally in this infinitesimal setting, it's a very straightforward problem. We don't know how to solve this. If you wonder where this is coming in, it's coming at the point where you were trying to show that you have two splittings of the Azumaya algebra on the graph of the zero section and on the graph of df. You want to show that the two splittings agree on the non-trivial, on the underived intersection. We know that this is true going through August and Vologodsky's proof, but we don't know how to prove this. I have a conjecture here, for if anybody cares about characteristic P methods. It uses the Artin-Hasse exponential. We have a conjecture for what the formula is, but we don't know how to prove this, so who knows what. But yeah, let me maybe stop here.